Welcome to the Experimental Math Seminar of Rutgers University's May 1st. Today we have a double feature. The first talk is by Pablo Blanco. The second talk is by Aurora Hiveley. As usual, please unmute yourself unless you have a question or comment. Go ahead, Pablo.
Thank you. I'll talk about generating functions for enumerating spanning trees in joint work with our very own Doron Zeilberger. So I'm going to give you kind of the layout for how what we did basically. So we found a nice graph family. You can think of it as a graph sequence, really, but I'm going to say family just so there'll be some sequences floating around. So now with those graphs in the sequence, we're going to count the number of spanning trees. I'll go into more detail later. And then since the family was so nice, we know that the generating function for this sequence is going to be rational. And we can actually guess what it is because we've computed a lot of terms of the sequence. So we have enough data to figure out what the rational generating function is. And yeah, and profit. So first I should tell you what a graph is. You have vertices, which are kind of like dots, and you have edges that are between them. I think a good bit of you have seen graphs probably. And so a spanning tree is a tree that, so it's connected and has no cycles. So this is a cycle, for example. This is going to come up again. So this is a cycle on 5 vertices, what I've just drawn here. So in the previous slide, I had this tree. I randomly made this tree. Here's a spanning tree for it in blue. It uses all the vertices of the graph. That's why it's spanning. Now, when I talk about counting spanning trees in this talk, it's going to be labeled spanning trees. So here some of the labels in this these slides are a little hard to read. So I've labeled the vertices 1, 2, and 3. So the labels are going to matter when I'm counting them. So this graph here is called K3, and I have 3 spanning trees. This one, and that one. And they look the same, but I count them differently because, for example, 3 is in the middle of this path, this blue path here. 2 is in the middle of this one, 1's in the middle of that one. So, I mean, this is the convention we're going to use, but how do we actually count them? We can use Kirchhoff's matrix tree theorem. So what is this? It uses something called the Laplacian matrix of a graph. And let me tell you what this is. So on the diagonals of the matrix, well, first let me label the matrix rows and columns. So first row and column is going to be V1 and then V2, Vn. I'm going to label my vertices V1 through Vn. The diagonals are going to be the degree of the vertices, so how many edges are coming out of that vertex. And then the off-diagonal, the non-diagonal entries it'll be like an indicator. It'll be -1 if there's an edge between these 2 vertices, the corresponding vertices, or it's going to be 0 if there is no edge between them. So let me give you, right. So once we have the Laplacian matrix of a graph, we still want to compute the number of labeled spanning trees. So how do we do this? Well, I take my Laplacian matrix, I choose an entry, I can take out the column and the row, and that's going to give me a smaller matrix. Take the determinant of that, and that'll be your number of spanning trees of the original graph G. So it's pretty amazing. You can actually do this for any entry, but for a project, we just picked like the last one, or I don't know if it was the first one or the last one, but just easier. So let me walk through an example for computing this number of spanning trees using this. So before I had, let me move this over here. You can't see that, so it's fine. Before I showed you this graph K3, and we know it has 3 spanning trees, so I better get 3 spanning trees when I run through this example. So here's the Laplacian. So V1 right here has degree 2. It has 2 edges coming out. It has an edge to, I'm having some trouble with these. There you go. I have to go with the mouse there. So it's adjacent to V2 and V3. So we have a -1 here and there. And all the other vertices look the same. So it's going to be the same thing to fill out the other entries in the Laplacian. Then I'm going to take out a row and column. So like this. And take the determinant. So 4 minus 1, 3. So like I promised, I counted the number of labeled spanning trees. So hopefully you believe this really small example. And that'll convince you for the application, just in general. So we considered several graph families, which are nice. The first one is going to, I call them powers of cycles because they're like they're the rth powers of cycles. I'm not going to define what powers actually are in this talk, but I think you should hopefully have a sense for what they are after I finish. So the idea is you take a cycle and, oops, you can imagine your vertices are neighbors that live on a street that is this cycle. And I'm only friends with those that live near me in this cycle. So if I have to walk really far to get to you, then we're not friends. So anyway, you fix an R value. In this case, I pick R equals 2. And I say I'm friends with you if I'm at most 2 away. So let's say I'm this vertex, number 1. Then I'm friends with 2 and I'm friends with 3 because I can reach them. I can reach this one and just using 1 edge, and I can reach 3 using 2 edges. So at most 2 edges I can reach you. So that gives me these 2 edges. I'm friends, so I have an edge. Edges represent friendship. And similarly, I can reach 5 by taking this edge, and I can reach 4 by taking these 2 blue edges here. So they're adjacent in this power graph. And you go along and now repeat for 2. So we were already friends here, friends there, friends there. It's a little more useful to see in a bigger graph like this one. So I'm not friends with, so this is still 1, but this is 4. I would have to, the underlying graph is going to be a cycle in this family. So like this. To reach 4, I would have to take this one and that one, and that's 3 away. I'm too far. We're not friends. So that's one family that we considered, powers of cycles. These are also known as, this is also a special case of circulant graphs. Circulant. So you might have also heard of those instead. And I impose this condition that my number of vertices is at least this big, so that basically my R is actually having an effect. If n is too small, then, for example, so generally, if n is large enough, then every vertex is going to have degree 2r. But if your n is too small, then that's not even going to happen. So we want n to be large enough to accommodate your r. And that's going to be one family. And then the same sort of concept, but with paths this time. So let me pick a big path this time instead of a small cycle like I did. Oh wait, this is also 5. Let me do this one, which is 7. And so it's hard to see the labels, but just know this one is, oh, why is that so big? Oh. This is 1 and that's 7, and it's labeled clockwise. So same deal. I'm friends. I pick r equals 2 again. I could pick r equals 3, but I didn't prepare a picture for that one. So I'm adjacent to 3 because 1 is adjacent to 3 because I can take this path in blue and it's adjacent to the one next to it. And you keep going around like before. But this time 7 and 1 aren't next to each other because you'd have to take this really, really long path. And it's important to note that these powers of paths are a subgraph of the powers of cycles. It kind of makes sense that they would be. So for example, this one, so this one's 6 vertices. This one's also 6. So keep your eye on the red graphs. This one is contained, this red one is contained in this other red one. And this is kind of going to show up. I suspect this is why some things show up later in your generating functions, but I don't know for sure. So let me define a generating function since I just said generating function. So if you have a sequence, A1, A2, so on, a generating function is a formal power series. So you take your sequence terms as coefficients and you just make a power series. Now, if our sequence satisfies a recurrence relation with constant coefficients, we call that C finite. And if you have to look back R terms, then we say it's C finite of order R. So a good example is the Fibonacci sequence. So you have your initial terms. You have to decide on some initial terms to begin with. Fibonacci sequence, you start out with 1, 1. And then to get your next one, well, you look at your previous 2 terms, and then you add. So this is C finite, and it has this recurrence. And it's order 2 because you're looking back 2 terms. So why am I talking about C finite sequences? Well, nice thing about C finite sequences is they have a good generating function, or a nice one. They have a rational generating function, in fact. And the denominator is going to encode your recurrence relation. So let's see, which one? So in the Fibonacci case, this corresponds to this, and this is going to correspond to that. Your numerator is going to depend on your initial values that you picked. So, for example, 1, 1 in the Fibonacci sequence, those were, we kind of decided on those in a sense. Now, for the graph families that I spoke about, the nice thing about them is that you can encode them into some finite state machine that's going to ensure that the sequences we talk about are going to be C finite. I'm not going to go into too much detail on that, but yeah, so it's transfer matrix method, I believe. So let's review the plan, what the plan was. So we found some nice families. We know how to count the spanning trees using determinants, basically, of the Laplacian matrix. So that means we can use Maple. We used Maple. You can use another program if you want.
No, you can't. I won't talk to you.
Yeah. So you use Maple to make your graphs, and then you compute the Laplacian matrices of those graphs. And you can count the spanning trees, the sequence of number of spanning trees for each graph. And now you have a bunch of data points that will correspond to, that you can use to guess your rational generating function. Because it's rational, so you can just fit your data. Now, we actually didn't only count number of spanning trees, we also counted total number of leaves in a graph, and even looked at sort of the ratio between them. So yeah, that's what we did. And we came up with some new sequences for the OEIS for counting. Now, here they are. Here's some sequences to be added. Some generating functions. Something that there's a few interesting things about these generating functions, actually.
Those are very hard to see. Can you make it larger?
Okay. Yeah, it looks like I can actually. Is that a little better?
Yeah, it's better.
Okay. Better, not the best. I think that's my limit. They're not very high res, unfortunately. So here's the generating function for, this is paths, powers of paths, when r equals 3. This is when r equals 4, r equals 3, r equals 4, for paths. These are paths. And the corresponding ones for cycles here, cycles. And you might notice a few things that are interesting. So if you look at R equals 3 for paths and cycles, you can notice there are some factors in common. I suspect because one is a subgraph of the other. So this is here and that's there. And this happens for all the ones we looked at. So here's this one, and this shows up right here, T6. And this one shows up over here. So that's cool. And also the coefficients are symmetric, actually. So here coefficient is 1, coefficients -4, -17, -17, 8, 8, 49. A little unusual. Same with the cycles, 1, all of them have this property, their factors. I think I'm running out of time. Anyway, we also counted total number of leaves. You can do this by picking a vertex and deleting it from your graph, and then you ensure this vertex is a leaf so you can find the spanning tree here, and you can add it back in to ensure it's a leaf. That's kind of the idea with counting total number of leaves. So it's still counting spanning trees, counting total number of leaves across all spanning trees. So we were able to do this pretty easily. We're able to exploit some symmetry in some graphs, like powers of cycles. All the vertices look the same, actually. So you don't even have to use the sum because all your terms are going to look the same. You just compute it once, multiply by n. That's all I have to say.
Thank you. We have 1 or 2 minutes for questions. Any questions to Pablo?
Yeah, well, can I ask a question? Yeah, your denominator of generating function is factors, right? Has multiple factors. For C-finite sequences, this might also mean that your linear recurrence operator with constant coefficient actually factors. Did you? So my question is it the case?
It's the case that what? Sorry?
That you have recurrence, right?
Yes.
So and I suspect that it can be factored as a non-commutative product of lower order recurrences.
Yeah, but everything is commutative.
The denominator, that is the factor?
No, in this case, it's obvious.
The way that it factors there, isn't that how the recurrence will factor?
The denominator is really the operator. Yeah. For C-finite sequences. So yeah, so answer is yes.
Yeah, so but then this, lower order recurrence gives you some information about properties of your spanning trees, right? That there are families.
That's a good question. Yeah.
Yes.
There are subfamilies in your family of spanning tree with certain properties that are annihilated by this lower order factor in recurrence.
Yeah, that's a good comment.
Yeah. And I had comment you in your generating function, you start summation with 1. It is typically starts with 0, right?
Yeah, typically.
Yeah, okay.
Yeah, it's a convention.
Yeah.
But Pablo, let me just rebuke you for not mentioning a very important new constant. So maybe you should mention it.
I'll mention it. Okay. So new constant is you count, is it leaves on top? Yeah, I think leaves. So total number of leaves
for any given family.
Yeah, for any given family. You divide by number of spanning trees. So I don't need the absolute value, whatever. or cardinally. And then you normalize by number of vertices. And this is always, trivial is going to be a most one. And you can find this for families. Yeah.
And take the limit and then go to infinity.
Yeah, limits.
And what is the name of this constant?
Of course, BZ constant.
Thank you.
Yes.
Okay, thanks again. The next speaker is Aurora Hiveley, who will speak about Wordle. Thank you, Pablo. Go ahead, Aurora.
Okay, hopefully everyone can see my screen okay. I'm gonna make the video smaller so that I can see my own slides.
Looks good.
Great, okay. So my name is Aurora Hiveley. I am also one of Dr. Z's students here at Rutgers University, and I'm going to be talking a little bit about experimenting with permutation Wordle. This is based on a paper out of Princeton written by Samuel Cutine and Lauren Smithline, so it's based on their work. We're exploring it a little bit deeper. Okay. Let's go to the next slide. Okay, great. So we're going to play a game that's sort of a mix between Wordle and Mastermind, if you're more familiar with the board game. So I'm thinking of a permutation of length n, and your goal is to guess what that permutation is in as few guesses as possible. And after each guess, I'm going to tell you which indices of your guess, if any, are correct, and the game will end when you've guessed my permutation. And your goal is to do this in as few guesses as possible. So let's see kind of what an example of such a game might look like. Let's say without loss of generality, your first guess is always going to be the trivial permutation. I haven't given you any more information to go off of, so you might as well keep it simple. So let's say I'm thinking of a permutation of length 5. Your first guess is 1, 2, 3, 4, 5. Keep it simple. I tell you that 2 is correct, but everything else is in the wrong place. So now to generate your next guess, we're going to keep 2 in the same position. It would be a little bit silly to move it somewhere else, because guessing 2 in any other position will definitely be an incorrect guess, and you have to put something else in that second position, which will also be incorrect. So it would be a little bit pointless to move it around. We'll keep 2 in the same position, but the other 4 entries you can permute however you like to generate your next guess. So let's say your next guess is 5, 2, 1, 3, 4. We've kept 2 in the same place. Everything else is moved to a new position. Now I tell you 2 and 3 are both correct. So, okay, again, we're going to keep 2 and 3 in the same spot. We'll permute the other 3 entries. And your next guess is 4, 2, 5, 3, 1. And I tell you, that's it. That's the permutation I was thinking of. So you won the game in 3 guesses. So in order to give you some notation now to go behind this game, each one of our guesses will denote with a gamma, whose subscript is the number guess that we're doing. So gamma 1 is our first guess. And for each guess, we have 2 subsets of indices. We have the subset that consists of all of the correct indices for that guess and the subset of incorrect ones. And we'll denote this with an I for incorrect indices or a J for correct ones. So for example, on gamma 2, you'll see your correct indices were position 2 and position 4, where those bolded numbers are. And the other 3 positions, the first, the third, and the fifth, were incorrect. So we have our sets I and J. So why do we care? Well, this paper by Cutine and Smithline proposes the following strategy, and they conjecture its optimality, but I'll set you up for it and sort of define what this strategy is. They call it cyclic shift. We'll abbreviate it CS for the purpose of this talk. And cyclic shift is a strategy for this permutation Wordle game defined as follows. So we're going to take all of our correct entries from guess K, so from gamma K, we're going to keep them in the exact same spot for gamma K plus 1. So in your subsequent guess, we're going to keep them in the same spot. For all of your incorrect entries, I'm going to take them and I'm going to move them to the next available incorrect index to the right, or I'm going to increment the incorrect index. And this is a little bit weird. The notation is sort of confusing, so I'll show you an example of what I mean. So let's say we're going to play a new game. Your first guess, again, is the trivial permutation, 1, 2, 3, 4, 5. I tell you 1 is correct. Now to generate your next guess, according to this cyclic shift strategy, we're going to take those 4 incorrect indices, and we're going to move each one of them 1 to the right. So 2 is going to move 1 over, 3 moves 1 over, 4 moves 1 over, and 5 gets kicked off the end, so it has to jump back to the front, to the next open position to the right. So your second guess is going to be 1, 5, 2, 3, 4 in this case, after everything is shifted. Now, in your second guess, I tell you 1 is still correct because we locked it in place. We didn't move it, but 2 is also correct. So again, if you're going to generate gamma 3 from gamma 2 according to cyclic shift, we'll keep our two correct entries fixed, so 1 and 2 are in the same spot, but those entries 5, 3, and 4 are each going to move to the next available incorrect index to the right of where they already are. So 5 has to skip over 2, it's locked into place, and it'll take that index 4, the position that's currently occupied by 3. 3 moves into 4's position, and then 4 again falls off the end, so it actually jumps back around to the first available incorrect index at the front of the permutation. So your third guess is going to be 1, 4, 2, 5, 3, and I tell you it's correct, you're done, congratulations. So their conjecture in this paper says that cyclic shift actually attains the maximal probability of success in R many guesses. So let's say I tell you, actually, I'm going to end the game after 3 guesses because I'm bored, I don't want to keep doing this. This strategy has the maximal it attains the maximal probability of succeeding. So you have the best probability of completing the game in that fixed number of guesses. We can alternatively say cyclic shift has the smallest average number of guesses when you average across all permutations of length n. So if I try this strategy out for every possible permutation that Aurora could be thinking of, and I count how many guesses it takes, average it, it's going to be the smallest possible, or it attains the minimal value. And it turns out our conjecture is actually that it is minimum, not just minimal, but we're going to use that alternative version of their conjecture for the sake of this talk. So in order to formalize sort of what a strategy looks like, if we're going to do experimental math, we have to tell a computer how a strategy works. Like, what is a strategy? How do you tell a computer every round, I want you to generate the next guess according to this specific strategy? So we're going to formalize our strategies as a list of n elements, and each one of those elements is going to be a permutation of length equal to its index. So for example, S1 is a permutation of length 1, S2 is a permutation of length 2, and so on. And we're going to call this a strategy of length n, and it can perform on a permutation of length n that Aurora is thinking of. So a game on a permutation of that length. And we're going to generate gamma k plus 1 from gamma k using the strategy component whose length is equal to the number of incorrect indices that we have. And again, notation is kind of a lot, so let's see an example. We'll go back to the example from the previous slide. So we had a point where gamma 2 was 5, 2, 1, 3, 4, and I told you that 2 and 3 were correct. So your set of incorrect indices consists of 1, 3, and 5, because your first, third, and fifth indices are incorrect. So I have 3 incorrect indices. I'm going to use S3, or the third component of my strategy, to generate my next guess. One possibility is that S3 is the permutation 2, 3, 1. In that case, then your sub-permutation of your incorrect indices, which is 5, 1, 4 in this case, turns into 5, 4, 1 for your gamma k plus 1. And in that case, gamma 3 is going to be 4, 2, 5, 3, 1. But I could have something else, right? I never fixed in stone what my S3 is, and if I want to compare cyclic shift to any other strategy, I could consider what something else looks like. Let's say instead that S3 is the permutation 1, 3, 2. Well, in that case, our sub-permutation 5, 1, 4 will turn into 5, 4, 1, because that 1 represents a fixed point, so 5 is going to stay put, and then the other 2 will switch spots. In that case, my gamma 3 will become 5, 2, 4, 3, 1. So you can see how 2 different strategies, or 2 different strategy components in the same overall strategy, could give you 2 different guesses in the course of a game. So how do we formalize cyclic shift then in this notation, and what other types of strategies might we think about to compare to cyclic shift to sort of analyze its efficacy? Cyclic shift in this case is going to consist of permutations 1. We leave 1 there just for the sake of completeness. You're never going to use the strategy component 1 because you'll never have only 1 incorrect index, but we leave it there for the sake of completeness. We'll use it for the entirety of this talk, even though it doesn't really need to be there. Then all other strategy components start with 2 and go up through n sequentially and then end with 1. So we have 2, 1, 2, 3, 1, 2, 3 up through n ending in 1. We could also consider, instead of shifting all of our incorrect indices 1 to the right, we could go 1 to the left, and it would be essentially the same. It's symmetric. We just have to be consistent. We're going to focus mostly on right cyclic shifting for this talk, but it is important to note this left shifting does exist, and we would formalize that on the way shown on that second line for CS prime. So each one of our strategy components there is going to be n, and then 1 through n minus 1 in sequential order. So what other types of strategies might we consider? Well, we might think about cyclic strategies. And what I mean by that is strategies whose components are all cyclic permutations. So in this case, C1 is a cyclic permutation of length 1, C2 is a cyclic permutation of length 2, and so on. And as a reminder, cyclic permutations are generated by one cycle. So of course, C1 is always going to be 1. There's only one permutation of length 1, and it's there for completeness. There's only 2 permutations of length 2. One of them is cyclic and the other is not. So we're always going to use 2, 1 as our cyclic permutation for C2. From there, we have some options, though, right? We're going to have some more choices for what cyclic permutations we sub in for C3 and above. Although it is important to note that C3 actually only has 2 options. There's only 2 cyclic permutations of length 3, and they are right and left shifting components. So that's kind of interesting. And the motivation for looking at these cyclic strategies is, for one, there's no fixed points. So when I'm generating gamma k plus 1 from gamma k, I'm not going to be guessing any incorrect index in the same incorrect position more than once. That's sort of a waste of my time. I'm going to assume that that sort of strategy is suboptimal because, again, you can never finish the game if you're guessing the same incorrect index in the same spot more than once. It's also nice because this is a smaller scope than considering any old strategy under the sun. And of course, cyclic permutations are easier to generate if I'm going to be doing experimental math with a computer and asking Maple to come up with all of these permutations. And they're also easier to analyze because they've got these recursive patterns that go into them. So that's one reason we might want to just focus on cyclic strategies, although eventually we will expand our scope and we'll consider strategies whose components are derangements. In that case,
can I ask you a question? You keep talking about strategies.
Yes.
What's your basic model? Is this a one-shot thing? You're going to just do it once, or are you going to do it over and over again?
Absolutely.
What are you trying to optimize here?
That's a great question. So I'm going to fix some strategy and I'm going to apply it to, essentially, I'm going to run the game thinking of every possible permutation of length n. So we're going to play it once where the permutation I'm thinking of is the trivial permutation.
But you're assuming they're uniformly distributed. You're assuming that the person posing the puzzle picks a permutation with a uniform distribution, and their uniform random number generator is accurate.
Absolutely, yeah.
If you were doing it if you were doing it in real life, you might worry that you might try to guess what the random number generator producing these permutations is. And if you could figure out their rule, you could get a lot faster convergence.
Definitely. And by contrast, the person picking your permutation might know what the strategy is and say, hey, I'm going to make your life harder now because I'm noticing you're always right shifting. So I'm going to pick the worst possible thing. So you're totally correct. But we are just assuming I pick some uniformly at random permutation from Sn. I want to have the highest probability of succeeding as quickly as possible. Yes, right. That's a great question.
Good. Thank you.
Yes. So yeah, and then we could also consider strategies whose components are all derangements instead of just cyclic permutations. And in that sense, we still prevent any fixed points, but we're, expanding our scope a little bit.
You could also, since there's a distance measure on permutations, Spearman's foot rule, for example, you could take that into account too. But sorry,
No, absolutely. There's a lot to think about with this problem, which makes it really interesting. And this talk is really going to be more of a sort of cursory overview of a lot of the different things we've thought about, because there's clearly lots of room to play and experiment, which makes it really exciting.
Yes.
So another thing that we can do to sort of measure the performance of a strategy or analyze it is to encode it with a generating function. And the way that we'll do that is we'll encode f sub s, which is the generating function for a strategy s, as follows, where a coefficient a sub m is going to be the number of permutations of length n, where again, n is also the length of my strategy, so I'm going to fix some n across the board here. And a sub m is the number of permutations out of s sub n that are guessed in m many guesses by strategy s. And we say exactly m, not at least m, but exactly m. So for example, if I consider my cyclic shifting strategy of length 3, then I'm only worried about permutations of length 3. There's 6 of them. So I expect my coefficients to sum to 6. They do. That's great. There's one permutation that can be guessed in one guess. So you'll notice that the coefficient on the linear term is 1. Of course, that permutation is the trivial permutation. If without loss, you're always going to start by guessing the trivial permutation, then that's the only permutation that can be guessed in one guess. And that'll be true for any strategy, but we'll talk about that a little bit more later. Similarly, there's only one permutation that's guessed in 3 guesses, and it actually happens to be that permutation 2, 3, 1. So we have to shift right twice, or 3 times rather, to get to that permutation. And then the other 4 permutations are all guessed in 2 guesses. Some remarks about these generating functions. As I said before, for any strategy, the coefficient of the linear term will be 1. Doesn't matter what it is. The only thing we can guess in one guess is our starting guess, which we're assuming is always the trivial permutation for uniformity. The maximum degree of these polynomials is not necessarily fixed. For example, there are some strategies whose components are derangements where the game never terminates. So technically, the number of guesses that it takes to finish my game is infinitely many. So you would have an x to the infinity term in your generating function. So you could also consider, is there boundedness in maybe some subfamily of strategies? For example, in our cyclic strategies, do we have boundedness? I'm not totally sure. This is another thing that we could look into. We haven't looked into it too much yet, but just a cursory observation. And the other thing to note, which is actually really important and interesting, is that the coefficients of the generating function for cyclic shift are all Eulerian numbers. And this comes from Cutin and Smithline's paper. And their proof I won't go into detail with, but I'll give you sort of a quick overview of how they go about proving this. They use the language of exceedances. And so the exceedance set of a permutation is the set of indices such that the entry is greater than its index. And again, notation is weird, so I've given you a couple of examples. In the permutation 1, 3, 2, the exceedance set is just the index 2 because 3 is bigger than 2. Everything else, the entry is smaller or the same as its index. And in 2, 3, 1, both the numbers 2 and 3 are bigger than their indices, so the indices 1 and 2 are exceedances. And their claim is actually that cyclic shift guesses any permutation pi in 1 plus the number of exceedances of pi many guesses. And this relates to the Eulerian numbers because a n k is equal to the number of permutations of length n that have k exceedances. And again, I won't go through the proof. I need to omit it for the sake of time. I've only got 24 minutes. But if you are interested, it's in their paper. It's in section 3. It's not a difficult proof. It's just got some meat to it. So another thing that we could do to sort of analyze different strategies, especially because we know something about how cyclic shift behaves from their paper, is we could consider what we're calling inductively constructed strategies. And what that means is the first 1 through n-1 strategy components come from cyclic shift. So we're going to cyclic shift for the first n-1 strategy components, but our nth component is going to be, let's say, any old derangement of length n. And the idea is if we can test performance of all of these, maybe putting cyclic shift in the nth strategy component already gives you an edge. And then you can imply induction all the way down by having this sort of benefit of Sn being right shifting. So in order to test this performance, we're only going to consider set permutations, or Aurora can only think of permutations that are derangements. And the reason for this is that when I guess the trivial permutation first, I want to make sure that that nth strategy component gets triggered. So if I have any fixed points, I automatically move down to a smaller strategy component, a lower one, and I won't, induction takes over from there. So I want to make sure that Sn gets a chance to try something. And I'm going to stop when my set of correct indices is non-empty. So when at least one of my indices is correct, and then I want to know how long does it take before something is correct, and how many correct indices do you have at that point in time, and maybe on average across all possible derangements that Aurora could think of. So again, if I take one uniformly at random, how well am I going to do? Surprisingly, this inductive strategy, when I consider any possible derangement for my nth component, is the same. And I'll show you what I mean by that. So here's one example. You'll see in this table, the left column is going to include all derangements of length 4. And then for my 2 columns on the right, I have 2 different possibilities for my nth strategy component. That first column is going to be my standard cyclic shift right shifting. And my last column is going to be a possible derangement strategy. In this case, it's the swap 1, 2, 3, 4. And because my first guess is trivial, I've also given you what gamma 2 will be according to this permutation. So I know that nothing's fixed because I can only play the game trying to guess derangements. So this is what gamma 2 is going to look like right underneath Sn. And then you'll notice in the table I've filled out the sets J2, or the set of correct entries for each permutation. And it turns out that if you sum the number or the sizes of J2 across all of these derangements, you count how many things there are that are non-empty. In both cases, you'll get 12. And if you average it across all of the derangements, you'll get 4/3. And this is true for any derangement. Although you'll notice that the distribution is different, right? So in my left column, I have two permutations who have empty J2s, and I have some who have singleton J2s. But in my far right column, I have 4 that have empty J2s, and I don't see any singletons. So the distribution of these correct entries are different, although across the board, on average, they're the same. So our claim is that if we average over all derangements of length n and we measure the size of J2, we're actually always going to get n over n minus 1, which again comes from the length of the permutation that I'm working with and the length of my strategy. So I think it was Ron Graham that said every math talk should have a joke and a proof, and ideally they're not the same, and it wouldn't be a math talk without someone quoting Ron Graham. So here is my mandatory proof. So we're going to say for any derangement D, which is going to be my nth strategy component, if I sum over all possible derangements that Aurora could be thinking of, those are my pi's, and I measure the size of J2, which in this case is going to be positions I, where Aurora's derangement and the inverse of Sn agree, I'm going to get n over n minus 1 times the number of derangements. So if I go back to the previous slide for a quick moment, you'll notice that gamma 2 is going to be the inverse of my S sub n. And instead of averaging, I'm going to count the total and then multiply it by that denominator, and I'm expecting to get the same thing. It'll just make my math a little bit easier. So in this case, in order to measure J2, I'm measuring matching entries between Aurora's set permutation pi and the inverse of my strategy component n. So we'll also recall that the number of derangements of length n, which is dn, is equal to n minus 1 times the number of derangements of length n minus 1 plus the number of derangements of length n minus 2. So just focusing on the left-hand side of the equation in our claim, we're going to swap in from summing over all derangements to summing over all indices, and then we're going to count the number of derangements that have agreement there. And for a fixed index I, we want to know, so say I'm focused on index I know what it is in delta. I want to know how many derangements pi have the same position I as delta. And so the way that we're going to count this is by saying if I have entry j in position I have 2 options, one of which is that then I is also in position j. So I have those 2 things swapped between each other. And in that case, I simply need to derange the other n minus 2 elements to create a derangement. So that's my second term there. Otherwise, if j is in position I, but I is not in position j, then I know that I is forbidden from being in position j, so it's equivalent to deranging n minus 1 elements, everything other than the thing that I know is in agreement, position I. So in that case, I have the number of derangements of length n minus 1 plus n minus 2. I'm summing over an index, but my summand is independent of I, so I multiply it by n, and then using my recursion, I substitute in dn over n minus 1, and then sure enough, I have the right-hand side of my claim. I suspect I'm running low on time, so I'll be very quick about my what's next future work section. Clearly, this inductive approach isn't going to work because we don't actually get an edge with right shifting. So our next focus is looking at the relationship between different components. Ideally, at some point, you get some sort of conflict or you get an edge later on. So let's examine that. Another assumption that we're going to make is that duplicated information is bad. And here's an example of what I might mean by that. Let's say that my 4th strategy component is that same derangement strategy from before. And Aurora is thinking of the permutation 3, 4, 2, 1. You guess the trivial permutation first, no correct entries. You apply S4, you get 2, 1, 4, 3, no correct entries. So you apply S4 again, and now you've looped. So you'll notice this is one of those cases of a never-ending game that goes on for infinitely many guesses, or until Aurora dies of old age and she can't tell you what the correct indices are for your guess. So we're making an assumption that this is worst case scenario, but duplicating information is inherently a bad thing. And a couple of other very quick observations from our generating functions. One is, again, all strategies have the same coefficients for the linear term. Duh, we talked about that already. And also the quadratic term, which is interesting. There's a proof about that. Maybe I'll talk about it again in the fall if I come back. We'll see. And then, of course, the coefficient of the cyclic shifting strategy for our cubic term is maximum over all strategies. Right now, that's just a conjecture, but we're working on some strategies, pun intended, about how to actually prove that. And thank you for watching.
Thank you very much for a very dynamic talk. Any questions to Aurora?
Yeah, I have a quick question. I would be very interested in doing this for an infinite permutation, where you're trying to you're given a sequence and you're trying to, an infinite sequence, and you're trying to understand it. It's an analogous situation, and it comes up all the time.
Yeah. Yes, obviously there's a lot that we can explore in this, and that's something that I hadn't even thought about yet, but I'll add it to the big long list of things that I'll probably look into until I graduate, and maybe even after that.
I'm also I like the infinite permutation. Don't you take infinity many times to guess?
Theoretically, yeah. I guess unless there was some nice pattern where like actually Aurora was just thinking of like 2, 1, 4, 3 forever, and you happen to guess that infinitely many guesses. It would be interesting to see how often do you actually terminate infinitely many.
Well, there really is a sequence of that we're trying to guess of distinct terms, a permutation of the natural numbers. So it exists. Okay. It's got a mathematical definition, and we're trying to find out what it is. So it's an analogous question, but for an infinite permutation.
Or whether you can guess it. Yeah, good question. More questions?
Or can you converge to it? Yeah.
Oh, yeah. More questions to Aurora? So in the inductive strategy, you have some empirical evidence, right? That it's optimal, right?
Yeah, I didn't mention any of that, but we've proven, at least experimentally, that their proposed cyclic shift strategy is optimal for all strategies whose components are cyclic up to, I think it was n equals 7, and derangements up to n equals 6. And then for those inductive strategies, empirically, we've shown this last bullet point. So the cubic term has maximum coefficient. And interestingly enough, if you actually left shift for your final strategy component instead of right shifting, that one has the smallest, the minimum coefficient on your cubic term. And I think I've tested that up to n equals 8 or 9. And that seems to be true so far. So yeah, our conjectures have some legs, at least for small enough n.
Thank you. More questions, Aurora? Well, thanks for coming, and thanks to both Pablo and Aurora for 2 great talks, and see you in a week. The next talk is the last talk for the semester. It's about Joel Lebovich, who will turn 95 on May 10th. So I hope to see you then. Thanks. See you next week. And Stoyan, please end this talk. Bye, everybody. Thanks so much for coming. Thank you.